So the pie charts are good, okay? The pie charts are very good because they allow us to look at a physical situation and say, like, this is where I see the energy stored or represented or how it manifests itself. So if we go back to our original, understanding of this, I have this cart and I have this rubber band back here, and I'm going to pull it back and I'm going to let it go. All right? So what was going on in the original situation? So I have my cart, and we say we're pushing it against a spring because you can't really draw a rubber band. So that's the initial situation, and then here's the final situation. All right, so I'm going to draw my pie here. I'll draw my pie here. Perfect. All right. So tell me, in the beginning, what is the energy situation? Okay. Where is the energy stored, or how is the energy represented? Most in this case, where is the energy stored? In the spring. Good. What do we call that, Jacob?
Elastic energy.
So Jacob says, look, we're going to start off with elastic energy. Is it all elastic?
Yeah.
Yeah, for sure, yeah. Perfect. Then, so elastic energy is energy stored in springs or rubber bands or rubber balls or something like that. Cool? All right, that's the initial situation. Tell me about the final situation. Where is the energy in the final situation?
Thermal energy, kinetic energy.
What's that?
Thermal and kinetic energy.
So there's a ton of kinetic energy, right, because it's moving. All right, but I don't think it's all. Because it's really rolling, so we've seen this example lots of different times, right? And I love it. I think it's super instructive as to what we're trying to do. Makes a ton of sense. Yeah.
Why wouldn't the kinetic and thermal energy be half and half?
Well, we don't know the proportions, right? And the reason we don't know the proportions, that's one of the limitations of the pie charts, because we don't know the proportions. I think this is a low friction cart. So because the cart is so low friction, like when I let it go here, it doesn't really slow down very much, right? So I think because it's a low friction cart, you're getting only a little bit of thermal energy. If I was sliding the block, that might be a totally different situation.
Okay, so on an assessment, will the way that we like draw the proportions be like heavily weighted towards how many points we get?
No.
Okay.
And remember, it's not points. The 3, 2, 1 is, do you have expert understanding? Do you have beginner understanding? Do you have intermediate understanding? That's what those are. Okay, so here's the problem. I'm going to take off the rubber band. I'm going to bring my cart back. And how do I get it to go if there's no rubber band? How do I get it to go?
Push it.
You got to push it, right? So I'm going to give it a little push. So the situation is exactly the same, only different. So what I have over here, I have the same after situation. Cart's moving. A lot of kinetic energy, a little bit of thermal energy. But where did that energy come from? I mean, am I elastic? No, it wasn't moving. I mean, think about what the before situation looked like. You had the car, it was at rest. I'm about to push it. What's our fourth energy type that we haven't seen yet?
Gravitation.
It's gravitational energy, right?
Yeah.
So, where is the energy coming from? What's that?
I say the push, but I'm not sure which energy that would be.
So I love what Jacob said. He said, well, I know it came from the push. I just don't know which one of those energies this is. And that's because, Jacob, it's none of these. This is energy stored in a gravitational field, which means you got to be up a hill. This is thermal energy you get from rubbing. This is kinetic energy. That's the energy of motion. This is the energy stored in a spring or a rubber band. I am none of those things. So the pie charts, the point of my story is, the pie charts don't give me a good way to understand this. Right? The pie charts don't give me a good way to understand this. So what we need then is we need a new representational strategy that's totally going to help us be able to do this thing. Is that cool? All right. So what I'm going to do is I'm going to introduce you to a new representational situation, which I think is super cool. And we're going to switch from a different type, we're going to switch to a different kind of chart. Instead of a pie chart, we're going to switch to a bar chart. Now, let me draw it before you start drawing it, because it's got a lot of pieces to it. Okay? So we're going to use a bar chart. So over here, it's a bar chart. And then in the middle, there's going to be a circle. And then another bar chart over here. So this is our initial situation. This is our final situation. This vertical axis is energy. Inside here, we're going to draw the system. Okay? And this is called the energy flow diagram. Is that cool? Now, the energies that we could represent are gravitational energy, kinetic energy, or elastic energy. Same thing over here. How's that seem? All right, those are all the pieces, so you feel free to draw that. There's always paper right on this printer. I'm so sweaty by 6 hours. This always has like 4 jackets on. It's all right. Did you? Hardest part about being in the world is being who you are. The hardest part. Yes, ma'am.
Can I go to the bathroom?
Go very fast though, because I don't want you to miss this.
Okay.
Okay. All right, we good? Ready to go? All right, so now that you have the initial setup, what we're going to do is we're going to try to answer some questions. So what goes in the system is the question. Okay? So in the system, we're going to write anything that is a thing or a place that can store energy, or anything that shows the energy. That's what goes in the system. All right? So it's places or things that store the energy, or things that show the energy. So, tell me, given this situation here, is there a place where energy is stored, or something that shows the energy? Right? Say one out loud.
Elastic energy.
Sure. So elastic energy is the energy type. Where is that elastic energy stored?
Spring.
In the spring. So we put the spring in the system. Perfect. What else do you think goes in the system?
Kinetic energy.
So kinetic energy is another energy type that we notice. How do we notice the fact that there's kinetic energy?
Because it's moving.
What's moving?
The cart is moving.
So because the cart is moving, that is a thing that where we notice the energy, so we're going to put the cart in the system. How's that? Now, this is going to take a little practice. That's no big whoop. We don't mind that it takes a little practice. All right, so we got spring energy and cart energy. So let's go to my initial situation. Where's the energy?
Spring.
It's in the spring, right? What kind of energy is that?
Elastic.
It's elastic energy, so I'm going to put a bar on my bar chart at elastic energy. How's that look? Is that cool? Now, one of the things that we do here to help ourselves understand is we oftentimes break it up into individual blocks so that we can, if it switches over, we can see how the blocks separate. So let's use 4 blocks in our bar. Does that sound okay for now? If we need more, we can go more. If we need less, we can go less. All right. Next question. Is there anything else in our initial? I don't think so. What's going on in our final situation? Okay? What's going on in our final situation? Yeah?
We have a thermal and then mostly kinetic.
So if we have 4 to start with elastic, how many do you want to say are kinetic?
Kinetic, I'd say 3.
3's good. That looks great. Now, we are missing one, true? But Noah already told us where it is. Where is it?
No, sorry, thermal.
It's thermal, right? Here's the problem. Thermal energy is not gravitational energy. It's not kinetic energy. That's not elastic energy. Where is the thermal energy? So here's the thing about our thermal energy. As the car rolls along the track, there's rubbing, correct? And when you rub, you generate this thermal energy that you can feel on your hands. But that thermal energy is readily dissipated. That means given off, given away to the surroundings. Right? The air gets warm, or the track gets warm, or the car gets warm, but then it just gives it off to the air and the rest of the surroundings. We can't store thermal energy. Okay? You can't store thermal energy. So, the thermal energy is not in the spring and it's not in the cart, it's not in the system. And so because it's not in the system, we say that we lose out of the system 1 block of thermal energy. Does this still work for us though? How many blocks did we start with? 4 blocks, yeah? And we end up with 3 blocks of kinetic and then 1 block of thermal. Is that 4 and 4? It totally is, right? And so that's why I like this representation. It's a little bit more sophisticated. It's a little bit more robust. But I still like the fact that the total amount of energy still has to stay the same. Okay. So what does that mean for this situation? So, we use the same setup, which I'm cool with. And the thing that's nice about this was we're using this as a comparison, so I know that the end situation is going to be the same. 3 blocks. We're losing 1 to the surroundings. Tell me what you think is in the system. Okay? Remember, the system is where we store the energy or how we notice the energy. What has to be in the system?
Kinetic energy.
So, kinetic energy is an energy type. Where do you notice the kinetic energy?
In the movement of the second card.
Good. Cart is 100% correct. And what's interesting is, I think that's the only thing in the system. Oh my gosh. I thought you were going to lose it all. I think that's the only thing in the system. If that's the only thing in the system, we got a real problem because we have 4 blocks of energy on the left side, correct? But we have no blocks of energy here. Is there any gravitational energy? What about any kinetic? Any elastic? So we don't start with any energy. Where did the energy come from? All right, check your neighbor on this one. All right, so turn to someone near you and ask them, where did the energy come from? Where did the energy come from? It had to come from somewhere. We got all this energy on the final side. Where did the energy come from? Check it, where did the energy come from? Where did the energy come from? How did the cart get moving? Yeah. Right? How did the cart get moving? Somebody had to push it, correct? And so what we say is there's no initial energy here, but did the hand supply 4 blocks of energy into the system? And the answer to that question is, yes, it did. And this is the reason why I like we call them bar charts. Last hour they called them LOL diagrams. It took me a long time to figure that out. They're like, we'll just do the LOL diagram. I'm like, what are they talking about? It allows us to add energy to a system or get energy out of a system. And that to me is, I think, is a very cool, robust way to represent the energy, which I think is cool. Okay? That is cool. All right, you ready to try another one? Let's do an easy one. I like one easy. So I have my cart. Okay. I'll push my cart. What happens to the cart after it leaves my hand? What happens to the cart after it leaves my hand? Goes up the ramp. What happens to its speed? Slows down until what? It stops? Are you sure?
Yep.
Are you guys agreeing with Jacob? Does the car stop? Oh, no. It's gonna stop and hit the thing. When does it stop?
When it hits the highest.
Good. When it hits its highest point, right? So like ready and stop. So I want to analyze the cart. Right after I let it go is the initial, and then its highest point is the final. Okay? So right after I let it go is the initial, and then at its highest point is the final. Okay? So here's the situation. So we know it's moving here. Up here it's not moving. Velocity is equal to 0. So this is the initial side. This is the final side. This is the system. This is the energy flow diagram. So I have some gravitational, some kinetic, some elastic, gravitational, some kinetic, some elastic. All right. I like it. So go ahead, sketch this up, and let's see if we can't figure out what's in the system. Where's the energy? Where are we noticing the energy? I love these LOL diagrams. I think that it just takes a complex situation and just makes it so it's understandable and like, oh, well, I know where the energy is.